Okay, good morning. So let's start. So maybe you checked your email this morning. We have good news for you. There's going to be a dinner, a school dinner, tomorrow, Wednesday, at 8 p.m. at Bovinus. So it's a churrascaria, meat place. So everybody's invited. You probably read the email, so it's on the school, except for alcoholic drinks.
No caipirinhas.
No, you can have caipirinhas, but on your own. So we'll start the second lecture of Marko on perturbation theory in LSS.
Thank you. Okay, so here on the blackboard I wrote a couple of, well, this is what we ended up with yesterday. Studying the equations of motion for the long wavelength fluctuations of dark matter. Here I suppress the long wavelength notation because we are now assuming that we are talking only about long wavelength fluctuations. And these are very standard equations that you find in all perturbation theory papers in the literature. So starting from like 80s, these equations were there. These are simple continuity and Euler equation. So remember, this theta was the divergence of the velocity field. We said that vorticity is not generated in leading orders in perturbation theory. We're going to neglect it for the purposes of these lectures. And in practice, usually you have to worry about it until you go to very high orders. Okay. So this divergence of the velocity is good enough for us for what we want to do. And then the equations of motion are given, written yesterday in this form. So on the left-hand side, you had only terms that are linear in the perturbations. So you see linear in delta and linear in theta. And these are the equations that you were solving last week when you were doing linear theory. If I just neglect all these complications on the right-hand side, I can just solve these simple differential equations, and I will get the linear growth of fluctuations. Okay. However, the fluid equations have also nonlinear terms, and these nonlinear terms are some second-order terms in real space. They become these complicated convolutions, well, not complicated, but whatever, some convolutions in Fourier space, where you have to take, for example, two fields which have different Fourier modes K1 and K2, and they have to be basically multiplied together through some kernels, alpha and beta. I wrote yesterday the explicit form for these kernels. And this explicit form from these kernels follows from the equations of motion for fluid. Okay. So crucially, something which is not very standard in the literature, and it was not there for a long time until relatively recently, and this development of the effective field theory for large-scale structure, is this realization that these equations for ideal fluid do not really by themselves make much sense. So what we are really doing is writing the theory for the long wavelength fluctuations only, and in the process of smoothing the density field and velocity field and so on, and writing down, smoothing these nonlinear terms and so on and so forth. There are some effective contributions which come as a source in the Euler equation, and they're coming from this effective stress tensor. I told you yesterday that we cannot calculate what this stress tensor is because it depends both on the long wavelength modes and short wavelength modes. But what we can do is to average over short wavelength modes because we are not interested in short wavelength. We don't observe them and we don't care about studying their dynamics because we cannot do it, we cannot see them, and so on and so on. And but still, what we can do then is to, in a sense, expand this stress tensor in the long wavelength fields only. And this expansion has some free coefficients, which are free functions of time. And in principle, they're not calculable from our perturbation theory. We have to either measure them in simulations or feed them from the data. Okay? And so this effective stress tensor has infinitely many terms, but luckily not all of them are equally important. There is an expansion parameter. There are actually two expansion parameters. One is that you're expanding in the basically density field. Okay, so you have, for example, here what we wrote yesterday were just the first possible terms that you can write down, which is the lowest order in perturbation theory, and they have the fewest number of derivatives acting on delta. Okay, so there are two terms, two kind of tensors you can write down, this one and this one. And of course, there are infinitely many terms which are either higher order in perturbation theory or they have more derivatives. I'm not writing them down, okay, because they're going to be suppressed. And on top of that, there is a stochastic contribution which comes from purely short scales. When you average over them, they still contribute some long wavelength fluctuations, but they're totally stochastic. They don't depend on the long modes. So you see, these terms, they do depend on the long wavelength fields. The purely stochastic term is there just because you have random realization of the short scales, which when you average can contribute to the long wavelength modes in a completely random way. Okay. So now this point maybe was not entirely clear, and yesterday we had a few questions about that also during the discussion. So let me start today by just making a simple argument to try to convince you what is yet another way. So here we came to this form of the stress tensor. I actually didn't derive it, of course. I just told you that if you, for example, start even from the ideal fluid equations and you do this averaging procedure carefully, you're going to end up with something like this. But there is another way to convince yourself that even without writing down any equations of motion, that short scales can indeed produce those kind of effects, okay? That kind of thing and this kind of thing, okay? So there is another general argument, and I'm going to try to explain what is this general argument now. I think it's instructive to do it. Okay, so imagine that, so this is the setup. Imagine that you have some, I'm going to do the most simple version of the argument, okay? But it will give you the idea for what is happening. So imagine you have some region of space, okay, of a typical size R. And now you do something in this region of space, okay? You have some distribution of matter in that region of space, which is given by delta. There's some overdensity, delta of x, okay? So you have some kind of fluctuations in this region, okay? Now, imagine that you, and let's say that these density fluctuations are calculated using perturbation theory, okay? You don't, for example, you never put these kind of terms, you just use ideal fluid, perturbative formulas, blah, 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 and you calculate some delta of x. Now, there is another delta of x in the same region, for example, which comes from simulations. Okay, so this is some other field, which is not identical, okay? There is a small difference. So now the question is, this small difference on short scales, okay? The small difference between the simulations, which are maybe the truth, let's call them the truth, and this other field, which you calculate in perturbation theory, how does it look like? Does it affect long wavelength modes? This is the question, okay? So this would be the analog of asking what happens when I have short wavelength fluctuations. Like how do they, for example, how does this difference between these two things affects long wavelength fields? And I think that maybe your intuition is that it doesn't affect at all, because whatever happens here, I don't care about it on large scales. But this intuition is not entirely wrong in Fourier space, entirely true in Fourier space. And let me explain why. So let us calculate. Let us calculate the following quantity. I'm going to call it stochastic delta of k, which is now the Fourier transform. So I'm in Fourier space, but it is a Fourier transform of basically the differences of these two fields in this region of space. Let's say that everywhere else is the same, so I'm interested in this region of space. So with some integral d3x, and I'm around this point here, which I may call the origin, so it's 0. So I'm doing some integral in this region of space, and I'm calculating e to the I kx, and then this difference. Okay? So that would be the Fourier mode, which comes from the difference between these two fields. And let's say that on large scales, these two fields agree, but on small scales, of course, simulation and perturbation theory are different. These are small scales that we're trying to average over. And now let's see how does this difference looks like when we go to Fourier space. So given that I'm interested in wavelengths which are much bigger than the size of this region, okay? I want to look at what happens for long wavelength Fourier modes. I'm not interested in short wavelength Fourier modes. So I want wavelengths which are much bigger than r. This means that k times r is much smaller than 1. I'm interested in the wave numbers which are such that k times r is much smaller than 1. So for this reason, I can expand this exponent here, okay? And so if I do that, I will get 1, I will get plus ik dot x, and there will be something which goes like k squared. So this thing is going to multiply this difference. So now let us see what are these individual terms, okay? So the first term, when 1 multiplies this difference, what does this integral actually tell you? Well, the first integral is just the total mass in this region, okay? In perturbation theory, for example, and the second one is the total mass in simulation. And if the mass is conserved, then this difference is going to be 0. So by mass conservation, we have that the first term drops, okay? So the second term also drops. It's a bit more complicated maybe, but you can see that it drops because x times delta basically measures the positions of the center of mass now. And if the center of mass in both perturbation theory and simulation coincides, then also this one drops. And this is related to the momentum conservation. And there is no general argument why any higher order term should cancel. These are the only two that are going to be canceled if mass and momentum is conserved. So therefore, this is really going to go like k squared. So you see, in other words, if I give you like a simulation box and I tell you split it into small regions of size r and reshuffle the particles inside such that you preserve mass and momentum of each cell, it's not that long wavelength fields will not change. They're going to change, and they're going to change by something proportional to k squared. And of course, there is some scale to make it dimensionless, which is r squared. Okay? This is a typical kind of term that you're going to get on large scales. So you see, this is an example where you can see that by general arguments, you do expect that if you have small like uncertainties on small scales, that they can leak to large scales. And this effective stress tensor actually captures exactly this kind of behavior, okay? And if you look, and this exercise is very interesting because first we learn that the purely stochastic term, so now this is purely stochastic fluctuations which produce some long wavelength modes which do not depend on the long wavelength fields. And if I want to calculate their power spectrum, the power spectrum, so P stochastic goes like k to the 4. Okay? So that is also a well-known result that the small stochastic fluctuations on large scales can produce some power spectrum that goes like k to the 4. So it is true that it goes to 0 when k goes to 0. So of course, you're influencing larger and larger scales by less and less, but still the thing is not negligible. Then it becomes a matter of how much precision do you need on each scale, and then whether you have to keep it or not is a matter of which precision you want to reach. So we cannot just neglect these things. We have to keep them. The second thing so this is the purely stochastic mode. But now, for instance, the difference between, let's say in this case, perturbation theory simulation may depend also on that, whether this region is in an overdense or underdense region. There is nothing in the symmetries or the laws of physics which forbids this. So for instance, if you have a long wavelength fluctuation in your simulation box, and for example, in perturbation theory, you do the same calculation, and then you look at this stochastic term here and the stochastic term here, it may be that the difference between the true truth or simulation perturbation theory here and here is different because it's modulated by the long modes. So for example, there is more growth of structure here, and there is a less growth of structure here. And so things can depend on the long wavelength fluctuations. And the fact that these stochastic modes also have a response to the long wavelength fluctuations is exactly this term. So you see, this piece is delta, and this is basically delta, just a tide. So these coefficients are, if you want, responses of how these stochastic terms look like to the presence of the long wavelength fluctuation of delta or long wavelength fluctuation of the tidal field and so on. So in other words, there will be also, by symmetries, by the symmetry argument, there will be also a term which is not purely stochastic, but it is basically the derivative of the stochastic term with respect to the long mode is non-zero. It can depend on the long mode. So therefore, there will be some term which is which basically looks like k squared r squared times delta long. Okay, and this is exactly the piece that appears in the equations of motions. It's right here. So this tau, this stochastic stress tensor, is going to have the power spectrum which goes like k to the 4. And there will be another power spectrum contribution which goes like k squared and then some r squared, typical size of the regions where things become nonlinear, times p linear, okay, coming from this delta. And here we derive this, averaging the equations of motion and so on and so forth. But there is a simple like symmetry argument which tells you that such kind of terms must exist. It cannot be that you write down your theory and just ideal fluid and that's enough. It is not enough. You have to add those kind of corrections, okay? And they have the same form as these terms here, as you expect, because they come from the same considerations. Here, we are imposing some mass, momentum conservation, and that is automatically imposed in the equations of motion, so it's not a surprise that we recover the same answer, okay? So this is a bit more intuitive maybe picture to see why these extra pieces are really needed. And if you ask yourself, what is a typical size of these terms? For example, how big is k squared r squared? How big is this correction? For example, if you look here, there will be some effective r squared, k squared delta. Okay, how big is this correction to the equation of motion? And if I tell you that typical r, what is R? R is some typical scale where your perturbation theory doesn't work anymore. So let's say it's a few megaparsec or something like that, 10 megaparsec. And if you ask how big is like your K that you're interested in, let's say K roughly 0.2 or 0.1 or something like that, you see that this term is significant. It's not small. It can be like, I don't know, 10% of the contribution to the equations of motion. So it's a big, important term. So whether you should keep it or not depends, of course, on what precision you want to reach, but it is not negligible, okay? So these are two different ways that you see that small scales really contribute on large scales. They really source large scales. And there is no way for us to calculate the exact coefficient or anything, because this is all about some very complicated short-scale dynamics, but we can parameterize it in terms of a few coefficients, in the same way as we do with the bias expansion. Okay, so that was some general comment about the equations of motion. Are there any questions about this? Is it a bit more clear or not? Probably not. Everybody looks very confused. Rogerio seems to be happy.
So you cannot distinguish L1 and L2, the effects from L1 and L2.
Not a disorder in perturbation theory. So here, this is a more general formula. And so, for instance, if you want to calculate things at second order and so on, then or you want to use it for the bispectrum and so on, then you can start distinguishing them. But on the level of the power spectrum, at leading order, okay, it is just this. Simply because in the equations of motion, to get theta, there are two derivatives here. And these two derivatives just contract with these things. They all become degenerate. But of course, like as you go to higher orders or higher loops or higher amplifying functions, and you keep more of these terms, you have to be careful about the structure of the stress tensor and keep them separate. Yeah. Here there is some effective parameter which multiplies this, and there is some effective stochastic term. And that is enough. So of course there are many other terms that I'm not writing, but this will be enough for the one loop calculation. There is yet another way to see why these terms are needed. Okay? There is a third way. Look, one way is just average brute force, and you see that these terms come out. The second way is think a bit about mass momentum conservation. These terms come out. And there's a third way, which is try to do calculations for correlation functions using only ideal fluid equations, and you're going to get nonsensical answers. Unless you plug in back these terms, things will not make sense. And we're going to show today that this is really the case. Okay? So the plan for today is really to find some solutions for these equations and see, for example, when we calculate correlation function, what happens. Okay? So is at least the big picture clear? So what we are trying to do is to see how the nonlinear dark matter field looks like. Okay? In the linear theory, it's very easy. You just solve linear equations. The dark matter fluctuations simply grow. Where there was an overdensity, there will be a bigger overdensity with time. They grow with some growth factor, and so on and so forth. But if you want to be a bit more precise, just one second. If you want to be a bit more precise, then we have to include nonlinearities. And my claim is that nonlinearities can be included this way, but also we have to keep track of these extra terms that are simply, for consistency, necessary. And now we are going to see, when we solve these equations, what do we get, for example, for the nonlinear power spectrum, and how does it compare to simulations? Yes?
I think the argument helps a lot, so thank you for that. The only thing that still bothers me is that we made the whole argument assuming the first place a long wavelength. So we assume in the first place that the lambda is much bigger than r, and that's where you come into the case
Yes.
where, so to some extent, we assume a long wavelength, and from that we conclude that the short scale mode will contribute to that case. So that's what's still.
Yes. So this of course has all possible Ks. If you calculate the full answer, you will get something on all Ks. I'm just saying here, let me focus on those Ks which are correspond to very long wavelength modes, because I'm trying to see how does small scale modes in some regional space, how do they influence long wavelength modes? I'm not interested in that, how do they influence short wavelength, because it's very complicated. So I cannot do anything. I can only ask myself, if I have some complicated reshuffling of particles here, but I preserve mass and momentum, does it influence, like, and I measure power spectrum again, am I going to get a correction on large scales? And there is a correction, because the two power spectra measured before and after reshuffling are going to disagree by these kind of terms. So that is the purpose of this exercise. And the statement then is that if you have just ideal fluid equations and you solve for your perturbation theory, these equations preserve mass and momentum. Then you do the full n-body simulations, preserve mass and momentum. This is an example where you have two things that are supposed to be identical, but they will not be identical. And they will always be different by these kind of terms. So therefore, to get a correct prediction, you have to add these kind of terms. And they naturally exist because of these arguments. So it's not our choice whether we want to keep them or not. They're really there. So we can choose to ignore it, but it will be bad. So I'll show that later.
So that's a question. So you mentioned that L1 and L2 must be fixed by simulation. That's cannot compute it from first place.
No, we cannot.
So you have to look at simulation and then you measure L1 and L2.
Yes.
So the question is, L1 and L2 depend on cosmological parameters?
Of course. Yeah. Yes. So first of all, let me also say one thing that I'll mention. There are many approximations that I did, and I'm not telling you the full story, because otherwise first of all, these are not strictly speaking just the functions of time. This is a very short comment I want to make. So that would mean that things are local in time here. Usually in quantum field theory, for those of you who are familiar with it, when we say that we separate scales in space, because space and time are basically the same thing, we also always separate things in time. So for example, if you have a short wavelength, like fluctuations in quantum field theory, it means that they're very fast. Their frequency is very high. While in cosmology, it's a very interesting effective theory, because here, like, all fluctuations, short and long, evolve with the same time scale, which is the Hubble time scale. So short modes, when they virialize, get a bit faster, but not much. So there is no parametric separation in the frequency, if you want. The frequency for everybody is Hubble. So this theory, strictly speaking, you can separate scales in space. You can decide who are the long modes and who are the short modes. But there are no such thing as fast and slow modes. So therefore, the short scales, when they evolve and produce this contribution to the effective stress tensor, at the same time, they evolve with the same time scales as the long modes. And so the long modes back react, and there is some complicated non-local in time evolution. So in full generality, theory is non-local in time. You, in principle, would have to put some integrals here which involve the whole history and so on and so forth. But for the purposes to make things simpler and not to go into too many details, let us imagine that, and in fact, this is true in leading order perturbation theory, you can approximate these things as just local functions in time. And I'm doing that simplification here. Yes?
Maybe I don't understand the answer to the previous two questions, because it looks to me that you only needed to expand the phase there in Miller expansion. And what you showed is that the two first contributions are not important for the stochastic perturbation.
Yes.
You don't have to assume k times r much more.
Well, because I'm just assuming that I'm looking at the Fourier mode for which this is true, such that I can expand this. Otherwise, because you see, x is smaller than r, so, but if I don't assume that I'm looking at the very long wavelength modes, then k times x can be as large as I want, and I cannot expand anything. So this is.
But this is the order k squared plus
Yes.
contribution. So what I'm saying is you don't have to use this fact to show that the first two contributions in this theory of expansion are not important for the stochastic perturbation, right?
No,
You
so
show that the first contribution should be the square term k.
yes, exactly. This is all.
Assume k to be k times r to be that small. Of course, if this is true, then this will be the only contribution.
Yes, no, exactly. I completely agree. So of course, it's maybe a question of limits, but yes, I'm really interested in the low k limit. I want to go to k going to 0. I want to look at the long modes anyhow, and then I'm just like expanding it from the very beginning. But I agree. So the first terms are vanishing. Yeah, that's correct. Okay, so that's good. So anyhow, coming back to the big picture, so we have the linear theory. Linear theory is good for CMB or early universe and so on, but for late universe it's not. Here we have some equations of motion, which include nonlinearities, and now let's try to solve them. Let's try to see how do we solve this. So now I have a dilemma, because solving these equations in full detail will require too much time, and I will not have time to talk about more interesting things. So how are we going to do this? This is, well, I'm fully aware that if I say, like, do it as an exercise, actually, almost in all lecture notes even, it is never derived, because it's really straightforward. I mean, there is nothing very difficult. I'm aware that you're not going to do it. So this is basically the problem. So one option that we have is that if you want, I can stay after the discussion session, and for those of you who are interested to see, I can do it on the Blackboard, okay, if you care about that. So we can do the exercise where I really do it, okay? The second option is that I do it now, but then it will be very sloppy, and maybe we don't have time to talk about more interesting things. Or the third option is that you cannot care less, and then, like, but I give an option for those of you who care, who are interested in these things. Like, maybe we can like meet after the discussion session, and it will take like maybe half an hour or so to show the solution. Is this acceptable? Yeah. Is this good?
Sounds perfect.
Okay, so is everybody happy with that? So I will continue now a bit faster, moving on and skipping this. It's very straightforward, but it is basically what I said yesterday. You find linear solution, plug it back here. You find the second order solution, plug it back here. There is nothing. So if you ever solved differential equations perturbatively, you know exactly what it is. There is nothing really very complicated. But anyhow, I want to show you a couple of notational things, some tricks, some things that you can see in the papers, and you will be maybe confused, like, where does this come from? And that would be a chance for you to see it, actually. All right, very good. So that makes things much simpler. So skip everything. Okay. Let me then make a couple of comments only. Can I erase this? Oh, this is so. Let's see. What should I say? First of all, let us focus on the case where omega matter is equal to 1. Okay. This is for simplicity. Everything can be done also in lambda CDM, but it is a bit more complicated. It requires to solve some like things numerically and so on and so forth. So here, when omega matter is equal to 1, these equations become very simple to solve. Okay, there is a very simple scaling of Hubble with conformal time, and so on and so forth. So this is a very simple example, and I'm going to work in this limit. But more generally, you can of course do things a bit more generally. Then the solutions are not going to be exact, like in this case, where you can separate space and time. You have to calculate green functions, do everything properly, blah, blah, blah. But in principle, it turns out that it is always a good approximation to approximate solutions in the following way. So this is going to be exercise that I'm going to solve this afternoon. More generally, we can always organize these solutions, and let me see what I want to say. So you can get solutions for both delta and theta, or velocity if you want. But let us focus on delta only for the time being, because we're going to be interested in the correlation functions of the density field at this point. And for instance, for delta, you can always say that delta nonlinear of, this is what I wrote yesterday, of k and some time tau is approximately, and I will explain what this approximately means, is approximately equal to sum of n goes from 1 to infinity in principle, even though we always keep a few terms. So there is a growth factor to the n power. So this is the linear growth factor. It comes out from the linear solutions. It's a growth factor to the n power times the nth order solution in this iteration procedure. Okay? When you solve equations iteratively, you will get nth order solution, which depends on k. And so now the question is like, so now why this is approximately true? Well, it's approximately true because equations are complicated, and it is not true in general that nth order will be proportional to the growth function to the nth power, because you have to be a bit more careful when you're solving these equations. This is true only in Einstein de Sitter. But to a very good approximation, it is true also in any lambda CDM. So if you use this as a solution, you're going to make 0.1% error. And nobody really worries about 0.1%, at least at the moment. So if you're worried about 0.1% for whatever reason, you have to remember that this is not the exact formula. You can go back and do a bit more complicated version of it. But for simplicity, let's say that this is good enough for us. So we're going to keep growth factor to the nth power. So why this growth factor comes to the nth power like that? Because I'll explain that today. But naively, it is the fact that when you put two linear solutions here, they're going to come with the two growth factors. So the second order solution will be proportional to growth factor squared, and then it keeps going on. Okay, it's a bit more complicated, a bit more involved. I'll explain it. Okay, so what is this nth order solution? So each of these guys is basically depends on n initial fields. Okay, so for example, the linear field is just proportional to the initial density field with the growth factor proportionality. The second order field will be proportional to some convolution in Fourier space of 2 initial density fields. The third order will be 3 initial density fields, and so on. So all of these guys can be written as an integral d3k1 over 2 pi cube, and so on, d3kn over 2 pi cube. There is always this factor of 2 pi cube delta of k minus k1 minus kn. And then there is f n of k1, kn. And then there is delta initial of k1, delta initial kn. Okay? And there is a similar expansion for velocity field as well. All right? So this is the structure of the solution. So again, what this means is that you take n initial Fourier modes. Then there is some complicated function of k's, which basically couples them together, tell you how to weight this product of these Fourier modes depending on their momenta. You couple them together, and then it is producing some k-dependent nth-order Fourier mode multiplied with the growth factor to the n. So this is your nth-order solution. Yes.
Because the equations are first of them time.
Yes.
So why do you need the information of any functions?
Sorry?
Why do you need the information of any functions?
N functions?
Yes, because it's for each mode is first of them time.
So this is not an issue of time here. So for instance, imagine that. Okay, so let's start our iteration process. So if first of all I want to do linear theory, I can neglect nonlinearities. I calculate the linear solution. Now I plug the linear solution as a source here. If I plug the linear solution for theta, linear solution for delta and theta here, then I have a differential equation where I have a second order solution, second order fields here now, and there is a multiplication of 2 first order fields here as a source.
No, okay, but the initial data is one function, right? Continues to be one function.
Oh, sorry, you're thinking, but maybe you're confused about, so it is one function in space, of course. So delta of x is some initial density field. But when I decompose into Fourier modes, okay, let me try to make a drawing.
No, I understand, but that equation is for each Fourier mode.
It is for each Fourier mode, but you see, these equations are nonlinear. So this means that you're going to couple all possible Fourier modes. So you start in the initial conditions with some small fluctuations. So delta initial in position space looks like that. So then what happens is that the time evolution makes it into very nonlinear field. So this is delta nonlinear as a function of x. So now, if I decompose this into Fourier modes and I want to predict this kind of thing, I cannot just linearly involve Fourier modes because this is not what is going to happen. I have to also couple different Fourier modes. Why do I couple different Fourier modes? Because, for example, if there is an overdensity here, there is a nonlinear term in the equations of motion which tells me, oh, velocities flow depending on you remember that in the equations of motion in real space, there are second order terms, like, for example, divergence of delta times v. So those terms are coupling all possible Fourier modes, and they couple them, and if you do it iteratively, you basically couple them to any order you want. Maybe it will become more clear this afternoon, okay? Is it clear what I'm saying? No, you're still confused about this.
For me, it's clear, but it's another problem. I'm talking about something different that I'm trying to stress.
Okay, sorry, but can you repeat?
I'm just saying that I understand that, okay, you're writing as a function of t, you made a decomposition t and k.
Yes.
Right?
Yes.
So, and now you're saying that we should have n functions for each k to solve the nonlinear at several times. But the initial function should be just a function, just one function. It's not an infinite set of any function.
I'm not sure to understand the question. So this is not that you have infinitely many functions. So you have only one function. So there is only one function here, which can be decomposed into d3k over 2 pi cube And then here there is like e to the I kx delta initial of k. Okay? So I have one function initially, and I'm just decomposing to Fourier modes. All that I'm saying is that the mapping between initial and final function requires you to do nonlinear transformation. The nonlinear transformation means a convolution in Fourier space. And this means like coupling all possible Fourier modes. But it's always the same field. It's always one field. I think that this is the answer. All right, today we're going to see how to calculate these kernels. For instance, let me show you one example, which is the simplest possible example, which is this. So the second order solution, F2 of K1, K2, is 5/7 plus 1/2 K1 dot K2 over K1, K2, K1 divided by K2. Sorry, this is a bit tedious, but can you imagine if we were to solve all these things? K1 dot K2 squared, K1 squared, K2 squared. So for example, this is how it looks like. So what does it mean? It means that if I want to calculate, for example, the second order solution for my perturbation theory equations, I will have to take two initial Fourier modes, couple them with this kernel. These are called perturbation theory kernels, and then do this integral. Okay? That will give me the answer for the second order field. And this thing here, so you can maybe recognize the building blocks, like this building block, and this building block, and this building block. They really come from the form of these kernels alpha and beta. Okay? They come from there. So because we have a coupling of different Fourier modes here in the nonlinearities in the equations of motion, then also in the solution, there will be some sort of coupling. And the precise form of this coupling and these precise coefficients, in the case of Einstein de Sitter, or at least this approximation, they come out to be these numbers, okay? So there's a non-trivial step to go from equations of motion to the solution. I'll do it this afternoon. But this is the second order solution. And you can find a similar expansion for velocity, and you can calculate these perturbation theory kernels at any order in perturbation theory you want, okay? Now, you may be afraid already and think like, oh my God, like looks very complicated. But then there are like simple equations which allow you to do it recursively, and it becomes very easy on the computer. So as I said, like each of these, every nth order solution for either for delta or theta can be expanded in terms of some kind of kernels. They're usually called Fn and Gn, okay? And there are some recursion relations which tell you that if you know all lower order perturbation theory kernels, there's some simple formula which combines all possible lower orders and gives you a higher order term. And so when you have a higher order term, you plug it back to this recursion formula and you calculate even higher order term and so on and so forth. So this fact that there are recursion formulas is not a surprise. It just comes from the fact that when you solve these differential equations, you do it recursively. You just basically plug lower order solution into the source and you calculate higher order solution. And this really is encoded in these kind of formulas here. Is this clear? So it's a very schematic thing. I'm just saying that if you take these different, so far we were neglecting these extra pieces. Like let's just for the moment forget about them. We'll do them a little later. But just pure nonlinearities, you can deal with them recursively, okay? And you can go to any order in perturbation theory you want. And it's not very difficult. At the end of the day, when you do calculations, you never go through all this procedure. You just open the paper, you find this recursion formula, F1 is 1, F2, G1 is 1, F2 and G2 are very simple, and then you start going further. You calculate F3, G3. It's a piece of cake. It takes like 5 minutes to write down the code that does it. So there is nothing complicated about it. But there is some story behind it, how to derive all these things, and I'll show you this afternoon. Okay, so this is the structure of the solution. I want to say a few words about the behavior of these perturbation theory kernels that is going to be relevant for later. I think that's an interesting thing. So this was one example of how this kernel look like. In general, it is always some rational function of momenta of this type. So what are some properties? Of Fn and Gn, okay? So first, if you send k, which is basically k1 plus kn, if you send this to 0, so in this example, it will be like if you send k1 plus k2 to 0, what happens is that Fn and Gn, they go like k squared. And this is again the fact of momentum conservation. So you see, if I'm sending the sum of this momentum, imagine I say that k1 plus k2 I send to 0. This means that external k that I'm looking at, which is k1 plus k2, is very small. And I'm looking what happens if I have like two large momenta, k1 and k2, are of course much bigger than k if k goes to 0. So what happens when I combine two wave number, two Fourier modes with large k's? What happens when I combine them, and what kind of contribution they produce for the long wavelength combination when k goes to 0? And this, as we saw from the general argument, this must go like k squared, and indeed it does. Because of course, this is encoded in the equations of motion. There is a momentum conservation. Okay?
What about the 5-7? There's some constant.
Oh, they all cancel. This is a very important, very good. So this is a very good question. Like if you naively look at here, so like, well, if I send k1, if I set k1 plus k2 to 0, okay, I don't know, there will be some constant terms. But no, they all cancel. You see, they all conspire to cancel because they have to by mass momentum conservation. They have no choice. So nothing is obvious. This is one thing that is going to be a recurring theme for the rest of the week, that many non-obvious things from these perturbation theory kernels actually turn out to be true because there is some secret machinery behind it. Okay? It's not a random coefficients. They come from the equations of motion that know about symmetries. Okay? So that was the first property. Then, let's see, there is another miraculous. Another important property is that I fix k. So I fix some external momentum k that I'm interested in, but then I send one of these k's to infinity. Okay. So choose some, let's call it p, and send it to infinity. Okay. So then, let's say kernels Fn, which looks like this. There is k1. There is kn minus 2. There will be p and minus p. So if I'm fixing the sum, the only way to send one of the momenta to infinity is basically to have this kind of situation. Okay? This goes like k squared over p squared. So the kernels decay when you send any of the momenta inside to infinity. Okay, keeping the external momentum fixed. And finally, there is the most interesting property. Yes? Sorry. Thank you. This goes to infinity. Or in principle, what it really means is it's much bigger than k. This is what really matters. Yeah? Thank you. Thanks. And finally, the thing is that if I send, for example, I choose some p such that it is much smaller than all other k's. I send one of these momenta to 0, basically. What happens then is very interesting. Look, so Fn of, let's call it K1, and then there is some P, Kn. I can choose any one I want. That one goes to something like this. There will be Pi divided by P squared. So there is a divergence. You see, when P goes to 0, this becomes very large. And you can see this thing explicitly in F2. So for instance, imagine that we send K1. So if I take F2 and I say, let me imagine that K1 is much smaller than K2. What happens then? This term is of order 1. This term is always of order 1 because there is the same power of K1 in the numerator and the denominator. But look at this term. So here, we're going to get, if I focus on this term, we're going to get K1 dot K2 divided by K1 squared. And so therefore, this contribution just grows as I make K1 smaller and smaller. It's a divergent contribution. However, any endpoint function that you calculate will never be divergent. And the reason why this happens, that in perturbation theory, we have these divergences, but in the correlation function, they all conspire again to cancel, is also extremely interesting, okay? And we're going to talk about that tomorrow, okay? The whole lecture will be about studying these kind of terms. Like, what do they do? What can we learn from them? And how, so these kind of terms are exactly the terms that are crucial, for instance, to explain, so this is a correlation function in real space, to explain why the BO-peak from the linear theory becomes very broad in the nonlinear theory. The reason for this broadening are these kind of things. So they're very important, okay? Now it all looks very abstract. Like there is some nth-order solution, there is some perturbation theory kernels, there is some mass momentum conservation, some formula, what is this? But it will all become very practical very soon, okay? So to understand what is behind that kind of physics, these properties are crucial. Yes?
So when you use delta n in terms of integrals of delta 1, you assume that delta 1 works for all k. So is that a problem?
Yes, this is a big problem.
So we need to somehow, I don't know, make a cutoff.
Oh, absolutely. This is excellent. This is an excellent point. This is an excellent point, and the rest of the lecture today, and probably a part of it tomorrow, is exactly about this question. Okay, it's very good. So let me just maybe say what you're pointing out is that here we have integral over all possible k's, and we are doing convolution of these Fourier modes at all possible k's. But I just told you should not trust your perturbation theory on small scales. So how do we make sense of these integrals? Okay. And this is the next thing that I want to talk about. Very good, so thanks. Okay, so here we have like some general equations of motion. What I was describing here is only the complication that has to do with the nonlinear parts. But of course, there is also a contribution that comes from these counter terms, from these pieces of this effective stress tensor, okay? And so let me just add them here. So they're much easier to deal with because you see they're linear in the density field. So that is very easy to deal with, okay? The nonlinearities are complicated. They require some convolution, kernels, and so on. But these kind of things are very easy, okay? So yesterday, you asked, like, how come that we are keeping only linear terms in delta? Why not nonlinear ones? And the answer is that there is this higher derivative piece here also, because there is a k squared times that, okay? And also tomorrow, probably, we're going to see that this is actually suppression, which makes it small enough that if I keep even higher order terms, that will be completely irrelevant for the one-loop calculation. So luckily, these are very simple to deal with. And usually, what people write down, the usual convention is this. I'm going to change notation now. So that is a bit annoying, but what can I do? So the leading order terms to the nonlinear density field, so this is leading. From tau yj. So the leading orders here are something which people usually call CS squared of tau times k squared times delta, well, let's call it initial, and then plus j, okay? This is a notation that you would usually find in the papers. So this CS here, squared, is basically almost the same as these two guys, except that there is also some time integral, there is some complication of how do you relate theta to delta and so on. This all has to do only with some Hubble, time integral, things like that. So just another function of time, which just comes out from this procedure. When I'm dealing with this, you see the momentum structure is always the same. It's only that I'm renaming this thing, processed a bit, when I find the solution to the equations, into some new function, which I call CS squared of tau. And then there is also some processing of this stochastic term, which I just call J. So what we know is that the power spectrum of J goes like k to the 4. That was based on the general argument. Okay, that is one piece of information that we have. Now, this is usually called in this literature the speed of sound. Okay, now it's a bit unfortunate, this name. It is called the speed of sound for historical reasons, because those kind of terms, roughly speaking, correspond to the pressure terms in the equations of motion, and they're multiplied usually with the speed of sound in the fluid dynamics. But the way you should think about this really is there is some scale. It has units of megaparsecs, right? So megaparsec square cancels this k to give you the dimensionless number. And so this is some scale which is roughly, it turns out in practice, and we're going to see that later, is roughly 1 megaparsec, okay? Or a few megaparsecs, something like that. So this is our perturbative solution to the equations of motion. And now let us see what do we do with it. Of course, what we want to do with it is to calculate some summary statistics. Yesterday, we had a long discussion about that from the data, what we really get at the end of the day, some summary statistics. And now, in theory, we have the full density field. And so let us also do some summary statistics. It's very complicated. You need all these convolutions, very complicated, very complicated, very complicated. But at the end of the day, we want something simpler. We just want the power spectrum, for example, for this nonlinear density field. All right. So let me indeed start with the power spectrum. All right. So schematically, we have that delta nonlinear is equal to delta linear. I'm suppressing now all these growth factors, k's, tau's, and so on. But just schematically, we have this perturbative expansion. And plus, on top of that, we have some CS square k squared delta linear and plus some j. Okay. But let us, again, forget about these two for the time being. So now, what do I want to do? I want to calculate some quantity which basically has delta nonlinear of k1 and tau, and then another delta nonlinear of k2 and tau. So this is what we call the power spectrum. Okay, this is what we want to calculate. This is what's going to depend on cosmology and so on and so forth. And this is what we want to compare to the data, either from simulations or observations and so on. So let's see what kind of things do we get here. So now, to calculate this quantity, we have to plug here the full expansion, perturbative expansion, and we have to plug also here the full perturbative expansion, and calculate all possible cross products. Okay, very simple. So, for example, we are going to have terms which are delta 1 multiplying delta 1 from here, and this is nothing but just d square of tau times p linear of k. Is this clear to everybody? Do you immediately see it? I'm just multiplying, like here, I'm replacing the whole thing, and then there will be delta 1, delta 1. Delta 1, delta 1 has two growth factors, and the expectation value of two initial fields, which are linear, is just the linear power spectrum. And in fact, this is what you did the previous week. You would say, what is the nonlinear matter power spectrum in linear approximation? Well, it is only the linear power spectrum multiplied with some growth factor squared. So how does this formula perform when compared against n-body simulations? Now let us do this exercise. Oh, I completely, thank you, thanks a lot. This is indeed very important. So let me in fact keep it here. Thanks. K1 plus K2. And this, of course, is K1 or K2, it doesn't matter. Thanks, this is very good. Usually we drop this, but let me keep it because in other terms it becomes a bit more complicated. I want to show you how this 2 pi comes out. So when we compare these things to simulations, this is what you get. So what is plotted here, thanks. So what is plotted here? I took some n-body simulations which have very large volume. So the error bars are very small. So first of all, I want to tell you that these error bars in each k bin here are very tiny. Look, this is the 1% of the percent scale. Okay? So this is the ratio of the linear theory divided by the nonlinear measurement from simulations. So if the linear theory was perfectly correct, this ratio would be always 1, okay? And if this ratio, is, for example, is 1.1, this means that theory is 1% wrong, okay? So if I look at the linear theory and I compare to the n-body simulation, you see that the linear theory breaks down basically at the very beginning. So this scales is like maybe 0.02 or something like that. Already doesn't work at these scales. So now, up to which scales in the nonlinear matter density field linear theory kind of works depends, of course, on how big are your error bars. If you take a small simulation, which has huge error bars, then everything will look very good. I mean, you cannot tell that linear theory breaks down. But if you go to the limit, where you have very large volumes, then you can see that the data points, even at scales which are, let's say, 0.05 or something like that, the data points are far away from the prediction of the linear theory, which in this case should be the straight line. Okay? So this is to illustrate that if you go to all these large-scale structure surveys that we are discussing, that we were discussing yesterday, and that you're all probably interested in, are going eventually to survey a huge amount of volumes. Where you have a huge volume, you have small statistical error bars. And in that limit, it becomes very important to be very careful about how do you do your modeling for the nonlinear structure formation, okay? And you can see that example here. If you think that maybe linear theory is good enough and you're going to get away with it, that is not going to work for this kind of error bars, okay? So, but another thing that you can see here is that what I plot also is the estimate of the next two leading corrections that I'm going to discuss now. And you can see that this difference between the truth and the linear theory is roughly speaking of the order 1 loop. I'm going to explain what that is. And that is what you naively expect. So this difference is of the size of the next to the leading order corrections. And so we may still have hope that when we go to higher order terms and include those, we are going to bring our model is going to be more sophisticated, and these data points will go down. Okay? So this is the expectation. And so let us see if that happens. All right, so now there is another contribution here. Sorry, Rogerio. There is another contribution here, which is now next to this leading order, okay? Actually, there are infinitely many, but so first of all, let us forget about these guys for the time being. Let us pretend that we don't need this. Who needs, like, effective counter terms? Let's just do ideal fluid, okay? Ideal fluid is good enough. What are the possible terms that I want to write down here? Let's do it schematically first. So what are the things that I can write down? Well, I can write down all possible products, right? So for example, there will be delta 1 times delta 2. Okay, so there will be delta 1 times delta 2. There will be, I don't know, delta 1, delta 3. There will be delta 2, delta 1. There will be delta 2, delta 2. And then there will be delta 3, delta 1, and so on and so forth. So which one of these are 0? Sorry?
When it's on 1 plus 2, when it's odd because...
Exactly. So for example, this one is 0, you would say, and in fact it is true. And let me find it, this one. So why are they 0? So remember, like, what does it mean first order field and second order field? It means that I take one linear field and I correlate with the second order field from this expansion. And the second order field has 2 linear fields in it. So I'm correlated one linear field with 2 linear fields in initial conditions. But this is a 3-point function, and we know that in the absence of primordial non-Gaussianities, and as long as we assume that the initial field is Gaussian, the 3-point function must vanish. And not only the 3-point function, but any like odd n-point function must vanish. And so this is why, like if you have 1, 2, this is not going to give you anything, because at the end of the day, this expectation value will act on these random fields, and if there is an odd number of fields, it gives 0. And a similar thing here. However, if you have, for example, second order field multiplied with another second order field, then you have 2 initial fluctuations multiplied with another 2 initial fluctuations. When you take the expectation value, now this is not equal to 0 anymore. Okay? And the same thing for 1, 3. So basically, there are these kind of contributions which survive. And so so first of all, let's see, how many powers of the growth factor they have? 4, that's right. Because there's 1 growth factor here, 3 growth factors here, so it's 4 in total. And also here, 2 and 2, this is 4. So there is like plus growth factor to the 4 of tau. Now, the usual convention is that this kind of contribution is called 2-2 contribution. So there is something which is called P22 of k plus 2 times P13 of k. And P13 is this thing, when you have 1 first order field and 1 third order field, and 2-2 is when you have 1 second and another second order field. It's just a name. And again, there is like 2 pi cube Dirac delta of k1 plus k2. Sorry, this is k1. All right? And so now all that we have to do is to sit down and calculate this, what are these things, okay? And let me do one of them. Let me do P22, and the other one is really identical. I mean, there is nothing really complicated here. So of course, both of them are fourth order in the density field. And this is why we have to keep both of them. We cannot neglect one compared to the other. But all higher order contributions will have more density fields, and they're higher order. So our first guess for which kind of correction do we have to add is really just this. Okay? So we want to add P22 and P13. And so let's calculate one of these things. I mean, none of these things are complicated. It just takes some time. So for instance, if I want to calculate delta K1 at second order and another delta K2 at second order, this is going to be what? I have expectation value. Okay, first of all, let me do the simplest possible thing. There is d to the 4 of tau. That factors out. Then I have expectation value. So the first second order field is d3p1 over 2 pi cube, d3p2 over 2 pi cube, delta function of k1 minus p1 minus p2, and then delta initial p1, delta initial p2. Okay? Times the second field is P3, P4. Yes?
So your delta initial is the same thing as delta 1?
No, it is not. It is not the same. The difference, the delta 1, is the growth factor times delta initial. But you're right. In terms of statistics and k depends, they're the same. Yes. Oh, I forgot the most important thing and you didn't tell me. I know, this life is difficult. I mean, you don't have to copy all of these things. I mean, I would rather like you to focus. I mean, these are so simple. You can find this in any paper. I mean, there's nothing complicated. This is what we want to do. All right, so that would be the full expression. Okay, let me not go into all the details, but now, what is this expectation value? This is some assembly average, which is supposed to average all stochastic fields, okay? So there is nothing stochastic in these delta functions, these kernels, and so on. So the only things that this expectation value acts on are these deltas, right? It acts only on the initial density fluctuations, all right? So really, what we care about is this: delta initial P1, delta initial P2, delta initial P3, and delta initial P4. It's a Gaussian field. So what is the answer for the Gaussian field? Have you seen that already? I thought so, yeah. But so remember, the answer, if you have a Gaussian field and you calculate expectation values, is very simple. You just have to make all possible contractions of the density fields. And there are only 3 possible contractions here. You can either contract this one with this one, and then the other 2, or this one with this one, and then the other 2, or that one with that one, and this one. So there are 3 possibilities. And when you make a contraction of 2 fields, this gives you 1 power spectrum. Okay? So what we are going to end up with is the P linear of P1 times 2 pi cube. So you see, it's very complicated. P1 plus, let's say, P2. Okay? And then there will be another. So I do these 2 fields, and there are another 2 fields where I have P of K3, and then 2 pi cube, Dirac delta, sorry, this is P3, of P3 plus P4. Then there is a second term, which is P linear of. Let me contract this field with this one. So it's still P1. But now the delta function is different. I have P1 plus P3. And here I will have P2. But also the delta function is different. And there is another one. I'm not going to write it down. It's very similar. Okay, so there are 3 contributions. And now all that you have to do is to plug these 3 expressions into this integral. Now it looks very complicated. It's very long. But look, there are already 2 delta functions here. Okay. And there are 2 extra delta functions here. And when you do the whole thing at the end of the day, when the whole dust settles, you're going to be left with, and maybe you can do that as an exercise, because I don't think that I have too much time. But what is going to happen is that, first of all, this contribution will vanish. Why? Because you want P1 plus P2 to be equal to 0. And when P1 and P plus P2 is equal to 0, your K1 is equal to 0. So you're basically you're only making a contribution to the 0 mode of the density fluctuation. So this term just drops. It doesn't contribute to the P of K. The other 2 contributions, after you deal with all the delta functions, are actually identical. So the final answer for P22 is really, as a function of K and tau, is the growth function to the 4 power times, there is a factor of 2, because you have 2 identical contributions after you deal with the delta functions. And there will be 1 remaining integral, which is something like that. There is d3p over 2 pi cube. There will be f2 squared, because you're multiplying 2 f2s. And inside this kernel, there will be p, k minus p, and then p linear of p linear of k minus p. So there you go. This is the perturbative solution to 2. Yeah.
How can we trust the solution if you are integrating the linear whole spectrum in half K?
Just wait 1 more second. I mean, like, I'll come back to that. We cannot trust it, of course. This is absolutely wrong. It doesn't make any sense. But you see, now we understand it, but people were using this formula for two decades without paying attention to this. It cannot be trusted, okay? It's a very, like, yeah, like, you're absolutely right. We cannot trust it. And I'm going to come back to that, why we cannot trust it. It's a very important point. At the moment, as I said, I'm pretending that these terms are not there. So I'm just dealing with these more complicated looking like formulas. But eventually, we're going to see how to cure this issue of integrating where we're not supposed to. That will be the third way to realize that it's fundamental to keep these things. Okay? So everything makes perfect sense. But let me now just say that there is a similar expression for P13. You can just sit down and calculate again. Now there will be some, in fact, let me write it down. I think it's important. Let's see. Can I erase all this calculation? I think that you can probably repeat it yourself. There is really nothing complicated, it's just tedious. So P13 is going to be something like that. So there will be d to the 4 of tau. There will be now 3 times p linear of k, and then there will be some integral d3p over 2 pi cube f3 of p minus p and k, and then p linear of p. Let me just double check that I got this right. Yeah. So this one has a slightly different structure. It has one p linear outside, and that is very important. And the reason why there is one p linear outside is because you're multiplying 1, 3. So there is one delta of k, which is external k, and when you make a contraction with a third order field, it gives you p linear of k. While here, all the lines were internal. And so this is why the two momenta are sitting inside. So the two power spectra are sitting inside. So you now may think, oh, very good. So I had linear theory before. Now I also calculated these nonlinear contributions. So let us go and check how does it look like in, yes?
In this, when you just roll F3, is it P1 minus Q or is it K minus P?
It is P minus P, K. There are three momenta inside because
P minus
P and K. Yes. Sorry. So let us take a look how does this perform. So let us add to the linear matter power spectrum also this loop that we calculated. And so what we get is something like this. So it looks a bit better, okay? So if you look before, it was a complete disaster maybe, I don't know. Now it looks a bit better. These points are a bit closer to where they're to 1, where they're supposed to be. But still, it doesn't work. And the worst thing of all is that I'm cheating here a bit. I'm estimating how big is like the next to leading order. How big are two loop contributions? But you can see that now the difference is not of the size of the two loop contributions, which means that if you add two loop contributions, things are not going to improve. It looks bad. It is not going to be improved by just adding more and more terms in this expansion. Now, why is this? Well, it is because, as you were pointing out, we are doing something again which is a bit suspicious. It doesn't make much sense. We are getting some answer, but how do we know that we can trust this answer? Because these integrals here, they run not only over the long modes, but they also run to infinity. So they also run over the short modes. And who guarantees that whatever answer we get for the short scales makes any sense? Because perturbation theory formulas do not apply there. So you can take the linear power spectrum, put these formulas on the computer, calculate these integrals, and numerically, you're going to get some answer. But what gives you right to trust this answer? You're applying formulas at high p's where the theory is not supposed to work. Okay? So that is the reason why if you just do ideal fluid approximation, the perturbation theory will never converge to the true answer, no matter what you do. Okay? So this is yet another way to see that there is something wrong with keeping ideal fluid approximation. Okay? This is the third way to see that there is something wrong.
What if you cut off the integral at the scale where you think you should...
Excellent. So very good. Now we are getting into the... It's such a pity that there are only 3 more minutes, but I'm sorry. I'm super slow. I thought I'll go faster, but maybe what we can do is such that I can... let me see. I'll come back to your question. I'm not trying to avoid answering your question. So see, this is very interesting. Now we are getting somewhere because you see, at the moment you try to compare to the data, then like all your formula arguments and so on, then it becomes the real thing. So it's like it either works or it doesn't work. So very good. So what Rogerio is proposing is the following. We know that there is some scale up to which we can trust perturbation theory, some nonlinear scale, which was roughly the place where the variance of the density field becomes of order 1. Okay? So let us just evaluate these integrals up to this scale. That we can trust. This is the part of this integral which is trustable. The only problem with this proposal, and I think that it makes sense to do it as a first guess, the problem is that now your result will depend on this cutoff. So if Rogerio comes and says, like, I want to use such and such cutoff, and then you come and say, I want to use such and such cutoff, and they're different, we're going to get two different answers. But how can that be? There can be only one answer. So that is not, so you see, because you're introducing explicitly some cutoff dependence. And now we are coming back. So now this looks very similar to what we discussed yesterday, that what are we doing here effectively when we introduce the cutoff is we are smoothing the small scales. We are saying, I don't want to take into account small scales. I'm throwing them away. But how much I'm throwing away depends on the choice of my smoothing scale. Where do I put my cutoff, okay? But the promise of all these momentum conservation, stress tensor, effective theory, blah, 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 was that there is something which systematically deals with these things. And what is this something? Well, these are exactly our friends here. So these terms are going to do the job of absorbing all this ambiguity on your smoothing scale. And this is the normalization that you were talking about. So every time when you have a theory and you calculate these loop integrals, they're called loop integrals like in quantum field theory because there are some momenta which basically run from 0 to infinity. And so every time you calculate these kind of integrals, there must be another term in the equations of motion which will take care of this ambiguity, okay? And we derive that from some other way, but now we see that even in the explicit calculation, there is some need for some extra pieces. And in fact, if I go back here, now there is an extra contribution to the nonlinear power spectrum, which is minus 2 times CS square of tau, and then there is like k square, and there is p linear of k. And there is another contribution which comes from here, and we said that this contribution is some amplitude times k to the 4. Of course, this amplitude depends on time. Okay? So all that I'm doing is just calculating the power spectrum. So I'm basically calculating delta 1 times delta 1, and there are 2 terms. So basically, I'm going to end up with minus 2 times CS square, k square, and then p linear. And then this j, which is stochastic noise, doesn't correlate with anything except with itself. And we saw from these general arguments that jj is some amplitude times k to the 4. And of course, there are many other terms here that I'm not writing down, but these 2 are enough. And so now comes the point that miraculously, not miraculously, but it must be like that. If we did everything properly, it must be the case that if I look at these integrals and I look at the part when I'm integrating over very high p's, the form of these integrals must agree with the form of these counter terms. Okay? And that is indeed the case.
So these integrals are finite?
They're finite only, let me just say this. So usually when we talk about quantum field theory and normalization, there is always some divergence. We say there's something is divergent, so we have to renormalize. Here, all these integrals are finite, nothing diverges. But this is only because you have the linear power spectrum which decays fast enough. If you invent another cosmology, where, for example, there is no radiation dominance, and you have scale invariant power spectrum all the way to the end, all these integrals will be infinite. But if you run an n-body simulation, everything will be fine. So the truth doesn't care about your infinite integrals. And in fact, in that case, you would automatically see that some normalization is necessary. So some counter terms have to be added to take into account these infinities. Okay? So now this is all very sketchy. So tomorrow morning, the first thing that I'm going to do is to repeat like why these counter terms are really saving us, because that, I think, is a very important argument. I don't want to rush over it. But let me just finish by showing, and I think that this is very good because I'm not super late. Let me finish by showing what happens if you add these guys to the power spectrum. So what happens? So look, this was a situation with a linear theory. This is the situation where you do only ideal fluid approximation. And then when you add the counter terms, the points finally come down. So now you see that things are much better.
We have to fit for CS, right?
Well, but this is just the truth. I mean, like, what can you do? So I completely agree. So see, now this is a free parameter. I don't know a priori what it is, but I can choose it such that my points go through the points. Because you see, this story of the fitting, some people say, but now there is another extra parameter. It is true. But if you go here and you try to add more loops without extra parameters, it will never work. It will never converge to a true answer. So the issue is not that we need more calculation. Just the nature, very nature of dark matter is such that on large scales, there are some effective contributions which are not calculable. In the same way as in the galaxy perturbations, there is a bias expansion, and there is nothing you can do about it. So, yeah, yes?
But then the idea of effective theory is that you have this free parameter you feed, and then you can use for other predictions.
Absolutely. So the same parameter that appears here will appear in the 3-point function, the 4-point function. So there is some predictive power. On top of that, you're not using all this information to fit only CS. You will improve the constraints on other cosmological parameters. If I were to run MCMC with this data, now I can go up to here, and all my error bars are going to shrink. So I do gain by including this CS. It's not a complete waste of time. Now, this looks much better, because you see that the difference between the truth and simulations, sorry, the simulations and perturbation theory now is within some estimate for the two loops, okay? So now I have some hope, because if I calculate next to leading order, next to leading order corrections, then I can hope to bring this curve down even more, okay? And then I will still have to do all this calculation and higher order perturbation theory. I have to also do the stress tensor at this point and higher order perturbation theory. Things become more complicated. So I'm not going to talk about that, but you can find the details if you care about that in the literature. One very unsatisfactory thing about this plot is that there are these big wiggles. Look at the size of these wiggles. It's terrible. Even if you bring this curve down, so that on average, it goes around 0. These wiggles are huge. You're never going to. How can you make them go through the line? That is a big problem. Okay. So what does this tell you? These wiggles. So first of all, do you recognize these wiggles? Yes, these are BAO wiggles. But you see, they're not the full BAO wiggles, because their amplitude is very small, just 1% or so, which means that when we do these calculations, we basically take into account BAO wiggles. There are BAO wiggles in all these linear power spectrums, so they're taken into account. But somehow it seems they're not taken into account properly, because the line is not smooth. There is some, comparing the truth from simulations and our prediction, there is some residual wiggling, so we are not getting BAO wiggles right. This doesn't look good, okay? What we ideally want is a smooth line. And I'm going to show tomorrow, and maybe Thursday probably, how to get to this smooth curve without having these BAO wiggles. All right, so let me just say one more sentence and I stop. That I was showing the example to see. I mean, in this example, you can see that adding these counter terms really helps. And tomorrow I will say a few more details. But there is a much more rigorous test that you can do, which is not to calculate the summary statistics. So you see, yesterday we were saying calculating summary statistics is very good, but for some purposes, it is better to look at the full realization of dark matter field. If you take your simulation and run it, and you get a full realization of dark matter field, and then you take the same initial conditions and apply this perturbation theory formula and get nonlinear dark matter field from the formula, then on the level of realization, you can compare the two. So rather than comparing the summary statistics, you can compare each Fourier mode separately. And because you're using the same initial conditions, there is no cosmic variance. Okay? So this is a beautiful method to get rid of the cosmic variance first in the comparison, and second, not to compare some summary statistics, but every single Fourier mode. So all amplitudes and all phases must be correct. And when you do this exercise with perturbation theory, this is what you get, okay? So if you do ideal fluid approximation, it never goes through the points. You can do one loop, you can do two loops, thing will just jump up and down, it will never converge. However, if you add the counter terms, okay, one loop, roughly 0.15 or so, this is what we saw in the previous plot. If you do two loops, look, perfect, okay? So this story of doing some calculation really makes sense. It's not that we are doing some nonsense here and calculate random things. We are really doing something which is good, okay? And we are able to, in the most stringent possible way, like comparing every single Fourier mode up to k of 0.3, get the whole density field right. So any summary statistics that you calculate will be correct by construction. So these perturbative methods, sometimes people say, oh, but this is not going to work, it's too approximate, and so on and so forth. But it is not entirely true. I think that a lot of that comes because of all these confusions that people had about which terms to put, how to keep them, how to put them together, and so on. So if you do that carefully, if you include all these extra complications that we discussed, then things look very good, okay? And I maybe may say some more words about this method on Friday, because I think it's very, very interesting. But for the time being, let's stop here, and tomorrow we'll discuss a bit more about the structure of these expressions, how these counter terms cure these issues that we discussed, and then we will move on to studying the BO wiggles. Okay, thanks.
Okay, questions?
So if you want to include more loop terms,
Yes.
you should include higher order
Yes.
counterparts.
Absolutely. So I'm going to discuss tomorrow how to do this counting. It is not obvious, for instance, how to do the counting, how many counterparts you need. So there is one simple rule of thumb. I'm going to discuss it tomorrow, but in principle it's true. If you want to calculate the bispectrum, for instance, you will need extra counter terms for the one-loop bispectrum. If you want to calculate two-loop power spectrum and you want to be very pedantic, there will be extra counter terms and so on. But all of these counter terms can be easily generated. So remember, all that you have to do in stress tensor is to write down all possible combinations of di, dj, phi, things like that, okay? So it's very algorithmic. You don't have to think too much. So it's a bit tedious, but there is nothing very complicated about it.
Actually, two questions. I assume that if you go beyond the trispectrum and you go to other terms, you get diminishing returns. So the more you get diminishing returns, that means the more you add, the better you get, but on a decreasing rate.
Yes.
The second question, just to make sure I understand, what you said is, and I know you're going to come back to this tomorrow, yeah. We should not worry about the large piece, which yes. means very small scales, because that will be somehow compensated by yes. the counter term that we put there. However, I understand that that's very sensitive to the value of that coefficient A of tau yes. that multiplies. So, because that fell out of nowhere here today. So, yes. How do you determine that?
Okay, so regarding the first question, it is true that as in any perturbation theory, first of all, as you approach the nonlinear scale, you're in trouble. So we always in cosmology want to push to smaller scales. But of course, we cannot do that. I'm like, yes, you're absolutely right. We are going to be in trouble if we try to push to very high k. Also, if you go to higher and higher endpoint functions, including more and more loops, eventually, we're going to have so many free parameters that there will be a very small or zero return. I completely agree with you. And then it is a matter of practical thing to see really what is the optimal thing for some data analysis. And the answer depends on the volume of your survey, the size of the statistical error bars, what kind of effects you care about, things like that. So there is always a bit of like of a choice. Or let me do two loops or one loop. Let me include that or not include that. So there's always a bit of a choice, of course. I mean, in principle, you can always write down everything and it will be fine. Because even if you add very many counter terms, they're all very much suppressed in your Fisher analysis or data analysis. You will not see them, so it's all good. But it is true that there is always a bit of a balance. Regarding the second question, so for instance, it is true that so for the moment, this amplitude comes out of nowhere. but this amplitude is there really to absorb, if you want. The counter term always has a part which absorbs the UV dependence of the integral, and there is a finite piece which remains. And this finite piece is measured from simulations. Now, how do we estimate the size of this finite piece? Well, this stochastic term is nothing but one Hello term. Okay? So for those of you who are familiar with the Hello model, if you look at the Hello model for the dark matter power spectrum, there are two contributions, right? P of k. There will be one contribution which looks a bit like the linear power spectrum, okay, which is usually called 2 Hello term. And then there is another contribution which goes like k to the 4, which is the 1 Hello term. And then there's something in between, okay? You get a nonlinear matter power spectrum. So now usually, people, when they talk about 1 Hello term, they talk about something which is constant, okay? But remember, this violates mass and momentum conservation. It cannot be that distribution particles in the halo can produce something like that on large scales. Whatever it is, it must go like k to the 4. So the usual Hello model, indeed, I think it violates mass and momentum conservation. People are aware of that. Of course, in practice, this doesn't matter much because it's much smaller than the other piece that you care about and so on. But conceptually, the 1 Hello term really should go like k to the 4 for the dark matter particles. And so you can estimate somehow the size of this term by trying to match it to the amplitude of the 1 Hello term here where we trust the shape. So this gives you a rough estimate of how big is this. And indeed, this contribution is completely negligible for practical purpose, it turns out.
Okay. So I don't see any further questions, so let's thank Marko and have coffee. Beautiful. Very nice. Very nice.
Oh, it's going to get much better when we talk about BPA.